What if a robot could restock an entire shelf completely on its own? In warehouses around the world, manual restocking is slow and repetitive, inspiring our team to create an autonomous solution. Our robot was designed to identify, collect, and place multiple items into shelves of varying heights with full automation. Built under a strict $200 product budget and confined to a 200mm cube, it combines precise mechanics and vision processing to complete complex tasks efficiently. LED indicators display each operating state, collecting, transporting, and placing, while onboard sensors and coders maintain smooth and accurate motion. Through repeated testing, the robot achieves reliable pickup, consistent navigation, and precise placement across all trials.
Hi, I'm Brodie, and I was in charge of developing the mobility subsystem, which allows the robot to move accurately and reliably around the workspace. The system uses front-mounted drive wheels powered by 1 to 150 DC motors, controlled through a motor driver hat connected to the Pi. This setup provides both torque and speed for navigating tight spaces and traversing inclines. Encoders were used to provide accurate and reliable movement of motors. The main chassis is a lightweight 3D printed plate with mounting points for both controllers, battery, and item collection system, focusing on modularity, weight distribution, and accessibility of electrical components.
Hi, my name's Dan, and I was responsible for developing the item collection subsystem, which allows the robot to securely pick up and place products on the shelves. The mechanism uses a servo-driven gripper paired with an N20 motor with a 1 to 150 gear ratio, providing precise control for the lift system. The lift operates using a low-stretch nylon line chosen for its strength and minimal elongation during repeated cycles. A bottom limit switch provides homing so the lift always starts from the known position, and encoder feedback ensuring consistent motion. Through testing, I refined the motion profiles and servo angles for smooth, reliable operation, allowing the robot to handle items of varying weights and heights.
Hi, I'm Ben, and I was responsible for the robot's eyes, the vision subsystem. I developed an object detection pipeline using OpenCV on the Raspberry Pi that processes the live camera feed and performs HSV color segmentation in real time. My system identifies the bay and row markers based on their shape and groups them together to distinguish which row or bay that the robot is in. Distance and bearing is calculated using a tightly calibrated pinhole model, ensuring accurate distances without the need for additional sensors. I also implemented warp plane detection using perspective geometry, which allows the robot to know its position in the aisles and avoid collisions. These detections are given to the navigation system at over 10 times per second, letting the robot know what it's looking at, where it is, and where to go next.
Hi, I'm Sam, and I was in charge of the robot's navigation system. At its core, the nav system is a robust, autonomous state machine with a finite sequence of intelligent behaviours that helps the robot complete warehouse orders. Before full robot assembly, the navigation system was pre-validated in CoppeliaSim, where key functionalities were tested for full hardware integration. From the designated starting zone, the robot aligns itself with the picking station's adjacent wall, beginning the main loop. The main functionality loop uses a series of PID controllers to autonomously navigate to the picking station, picking up an item and safely travelling to a bay and placing the item. Dual PIDs were used in all precise vision-based movement, ensuring both the distance and angle were accurately adjusted to suit the location, as well as conditions for loss of sight. 3 status LEDs are also included, providing observers an indication of the current state. The result of all this? A modular, vision-driven navigation system that's robust, easily debugged, and ready for multi-order loops.
Integration is where all parts of our robot, mechanical, electrical, and software, come to work together as a single coordinated system. The modular chassis houses the Pi Pico and main battery at the rear, balancing and keeping stability during lifting. At the front, the gripper and lift mechanisms are positioned for effective object manipulation while maintaining stability. Power is managed across 2 boards, with a motor hat powering the Pi and drive motors, while a separate 5V converter supplies the Pi Pico and its peripheral. This allows the item collection system to operate independently or in combination with the rest of the robot. On the software side, the Pi Pico handles low-level motors and servo control for the lift and gripper. The Pi manages high-level commands, path planning, and sensor processing. The boards communicate over serial, allowing coordinated control while the robot responds to sensor inputs from encoders in the Pi camera. This integration of hardware and software enables the robot to operate efficiently and accurately, turning individual components into a single autonomous system.